Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. We're going to continue our discussion on modeling with binary variables. In particular, in today's lesson, we're going to observe modeling a fascinating problem known as the traveling salesman problem and solve it using the pulp modeling system and Python language. Let's get started. So the traveling salesman problem is one of the very important combinatorial optimization problem, which is very simple to state. It says that given a collection of n cities, along with pairwise distances between them, we need to find out the shortest way to visit all the cities and return to the starting point. So this is known as a tour. A tour is essentially you start from a particular city, we visit all the cities, and we come back to the starting point. So here's an example of a tour through the 42 different cities in the US. Okay, so let's formulate this problem as an integer program. So the first, we are going to introduce variables xij, which is going to indicate the following. Xij is 1 if city I is visited immediately before city j in my tour. And these variables are going to be only defined for when I is not equal to j. So what is our goal? We'd like to minimize the length of the tour. Remember that Cij is the length of going from I to j. And so this is the cost of Cij times Xij is the cost of going from I to j. And we sum it up over all the pairs of cities and we look at the total cost. What is the first constraint telling us? The first constraint tells us that for every city, if I look at city I, you must leave that city, right? Xij over all j is equal to 1. So there must be one city that you visit immediately after I. Similarly, for every city I, there must be one city j which you visit immediately before j. So I could have added the constraint that j is not equal to I, but those variables are not defined here. So these are two logical constraints, obviously. But then there is these additional constraints which I will talk a little bit more in detail about. These are known as subtour elimination constraints. So let's go into the next slide that talks about this. So let's look at this particular example. So here we have two cities, I and j. So now let's go back and talk about the subtour elimination constraint here. So what does it tell us? So let's read this off. So it says for all subsets of the cities of size greater than or equal to 2, it says that the number of variables that I choose that go from I to j should be less than the cardinality of the set minus 1. Right? So what does that mean? So let's see why we have this constraint. So suppose we have two cities. Now S is I and j. So what the subtour constraint tells us, remember it tells us that you have to sum up over all I in S, all j in S, xij, and that should be less than cardinality of S minus 1. So cardinality of S is 2, minus 1 is 1, that's this constraint, and we'll sum up over all I in S, which is I, j, and xji. So what does it tell us? That if you have between these two edges, xij and xji, you can select only one of them. So in other words, you cannot have a loop in your tour that consists of only two cities, right? Unless you have, because we have to visit all the cities and come back, so there cannot be any subtour. This is called a loop. This is a loop of size 2 or a subtour of size 2. Similarly, if I have three cities, xij, remember the right-hand side is cardinality of S minus 1, so that's 2. And then we look at all of the pairs, xij plus xik plus ji plus jk, and then so on. And among all of these pairs, you should not select more than two of those things, right? So that's what this says. So you could do this. I could have selected xij and xjk. That's fine. That's not a subtour. But I cannot select another arc because that would put in a cycle here. I could have selected xji, and I could have selected xik. That is also part of a tour, but I cannot select another third edge, which would make it as you would put a loop here, right? So this is what this tells us, that these are called subtour elimination constraints, which basically eliminate subtours. Now it is important to note that the number of subtours can be very large because we have to look at all possible subsets of size 2 or more. Okay, so there are many subtour elimination constraints. So the idea is what we're going to do is we're going to solve without any subtour elimination constraints. Then we're going to inspect the given solution to check if there are subtours. And then we're going to add the subtour elimination constraints corresponding to the found subtour, and we're going to repeat. So we're not going to add all the constraints at a time, but we're going to add them as needed. So here is a code using pulp to model this. Okay, so remember that we have to install pulp and the GLPK software before we can run this code. So here is a distance matrix. So here is an example with 1, 2, 3, 4, 5, 6, 7 cities. So this is a 7 by 7 distance matrix, which tells us the pairwise distances between city I and city J. This is not necessarily a symmetric matrix, but it could be. So the number of cities is going to be the length of this matrix, which is n. And n is the set, which is given by 0 through n minus 1. And now we're going to introduce an edge. Is a list of tuples, which basically I and j for all I in n, all j in n, if I is not equal to j. So we are going to define variables corresponding to each ij pair. That's what we're going to do. So first one, we create the pulp model, m, as before. Then we introduce these binary variables, or these variables. Notice that we are creating these variables as with this .dicts, as a dictionary. And so each of these variables will be called x, the corresponding to the set E, which is the set of edges, and they are binary variables. We create the objective to our model. So what is the objective? So we sum Cij times Xij for ij in edge. That's my objective. Now we're going to add constraints. Remember what the first constraint is. The first constraint tells us that among all the edges that leave city I, you have to pick one of them, exactly one of them. That's what they said. Sum of Xij for all j is equals to 1. The second constraint tells us that for city I, among all these edges that enter city I, you have to pick one. So these are the first constraints. We don't have any subtour elimination constraints. So we solve this problem, and we collect the objective function values. And now we have to check whether there is a subtour or not, right? So this function takes a solution, xsol, and then calculates a subtour. So let's see how it does that. So first of all, it sets a successor node to 0, and it builds a subtour by putting in 0 as the first item in this array, in this list. And while this is true, and then we're going to keep looping this, so the next node is going to be, if you look at the solution that starts at is the successor node to node j times node j, if this is 1, you're going to add it, right? So that's going to be the next successor. So we are starting from node 0, and we are seeing what is the next node that we visit. So perhaps we visit node 5, and then this becomes your successor node. We see that we visit node 2, and we visit node 1, and then we visit, if we come back to node 0, then we have found out a tour. That's a tour. And so we append this, and then we return this subtour. So now here is the subtour. So this is the routine that adds the subtour constraints and repeats. So first of all, we have a subtour array which calls a subtour function that we've just defined and checks and corresponding to that solution. If this subtour array is of size n, which means that we have visited all n cities, then we have found out an optimal tour. We return its optimal solution, and we break out of this loop. Otherwise, we print out the subtour that we found out, and then we add the subtour constraint. What is the subtour constraint? Well, for all the edges in this subtour, all the cities in this subtour set, we want sum of Xij to be less than the length of the subtour minus 1. We add this constraint, we solve the model, and we keep repeating this thing. And this loop gets repeated while this is true. So here is the output of the code for that little example. Please try it out. That first of all, it found out, remember there are 7 cities, right? So first out, it found out a subtour going from 0, 2 to 4. Then it found out a subtour going 0, 2, 3, 6, and 4, and then so on. And he added those constraints one at a time until it found a tour which covered all the 7 cities. And so it stops, and it returns optimal tour length. So we have just solved a traveling salesman problem. So in this lesson, we have studied a formulation of the traveling salesman problem. This is a specific formulation, and we have solved it using the pulp modeling system. There are various other alternative formulations which you might be interested to look at. That concludes this lesson. Thank you.